them, making them more reliable. And specifically, I want to introduce the problem of negative side effects. And then in the second part of the talk, I'm going to discuss briefly about some of the interesting results that we saw from our user study on how users are responding to side effects. And just to give you a glimpse of the technical approaches to mitigate the problem of side effects and how we can make the systems more reliable. There's a lot of interest in now deploying autonomous systems in the real world, and some of the common examples are robots that are operating in the warehouses, systems that can achieve human-level performance, or even better in some of the complex games like chess and Go, prototypes of self-driving cars, and even planetary rovers. These systems are called autonomous agents, and they are characterized by their ability to optimize a given objective or a goal through a sequence of actions, but without excessively relying on humans and without the human intervention to be able to achieve the goal. Now, the long-term goal of AI, in my opinion, is to be able to deploy these autonomous agents in the real world such that these systems can operate in a safe and in a reliable manner without having to rely on their human counterpart all the time. So you can see here the video on the left shows a robot in an indoor setting, and it's working fine with even fragile items. And on the right, you can see that we have autonomous cars that are interacting with other cars on the streets, interacting with pedestrians and cyclists, and it's able to operate in a very safe manner. This is some of the visions that we have for how the autonomous systems should be operating when we deploy them. We're making steady progress towards this goal, but we're not there quite yet. The current state of the art looks something like this. So this is a robot from Boston Dynamics that's been assigned the task of stacking the cardboard boxes on the shelf. This robot does a pretty good job of stacking the boxes, but also notice that it is operating in a somewhat structured environment. There's not a lot of clutter or disturbance around it. So let's see what happens when we deploy the same robot in a less structured, or what we call as unstructured environment. So it's the same robot from Boston Dynamics with a comparable box, except that it is operating in a slightly unstructured environment. And as you can see here, this robot is falling down, it's failing in ways that we could not have anticipated, especially after seeing how it performed in the more structured setting. So this video here is an example that shows that many state-of-the-art AI systems are specialized in performing simple tasks in the real world, but even then, they're reliable only when they operate in structured settings. In fact, what we see here is not an isolated incident. There are several media reports in the recent years that show that the AI systems are having some undesirable consequences that are discovered after we deploy them in the real world. So this includes Google's medical AI, Tesla's cars on autopilot mode, and many more. These systems showed promising results when we evaluated them in the structured setting. They showed promising results when we evaluated them using the benchmark data. But then once we deploy them in the real world, there are a lot of negative surprises that we did not anticipate. There's a lot of challenges in trying to guarantee reliable performance of the systems in the real world. And one important challenge that is important to address is when the systems are operating based on incomplete information. So what I mean by that is many of the AI systems are having some information about the target environment using which they decide what actions to execute and how they should be going about completing their task. But in many cases, this information is incomplete. And this could be because of many factors, such as the designer of the system may have accidentally overlooked certain details, thinking that it is not relevant to the task, or maybe they did not realize that it had to be encoded in the agent's model. Or sometimes the designer would want to have the details encoded perfectly, but the information could be unavailable during the design phase. There's also inherent challenges in learning and accurately encoding user preferences about how we want these systems to behave in various environments. And another factor that's hard to encode is the cultural differences between the development team and the target users. These are some of the factors that cause the AI systems to operate based on incomplete information when they are deployed, and this could significantly impact the system's performance. Another reason for unreliable behavior is due to the external disturbances and wear and tear. So what I mean by that is the system may be operating based on a perfect model, perfect information, but then the sensors that are providing the information to this decision component may have failed, could possibly because of wear and tear. And that could lead to unreliable behavior. So we now need to make sure that all the components that are providing input to the decision-making component are also reliable so that the system's decisions are reliable. And thirdly, another major challenge that we have now is we are deploying AI systems in a very broad context. So the systems are now interacting with people from very diverse backgrounds. And it's not clear a priori whether the decisions of the certain systems could impact a certain people in a negative way. So it's important to analyze the biases associated with the system's decisions and how it could impact different demographics. There's also a lot of interest now from the government, from the CS community, the research community, and of course our industrial partners. Everyone has acknowledged that this is an important problem to address, and it's not very futuristic. As we start deploying more and more AI systems in the real world, it has become a more important and immediate problem to address. So the key question that has motivated my research is how can we identify and mitigate the undesirable behavior of AI systems and enable them to operate in a more reliable manner when they are operating in open world environments. Now, before I go into the technical details of how to identify the undesirable behavior, I want to take a quick moment to explain to our broader audience on how these systems actually decide what actions they should be executing in each state or how they go about completing a task. So one way of doing that is by using automated planning techniques where the agent or an autonomous system observes the state of the environment, and then using its model of the world, it will select and execute an action that maximizes its reward. So the assumption is that all the important parameters, including its ability to observe a state, the reward associated with an action, and its model of the environment are all given to the agent before it starts to operate. The agent's behavior is determined by its policy, which can be treated as a mapping from states to actions. So the agent computes a policy, meaning that it knows what action it should execute in each state. So clearly, the model of the environment is a critical factor that can affect how the agent is going to operate. This model can either be handcrafted by a domain expert, or it can be machine acquired based on the data that's available. While we want these models of the environment to be as accurate as possible, in most cases, AI systems are operating based on incomplete models of the world, and primarily it's because it's practically infeasible to have perfect description of many of the open world environments. So in the rest of the talk today, I'm going to focus on unreliable behavior that arises because the systems are operating based on incomplete models of the environment. Specifically, I want to focus on the problem of negative side effects. Negative side effects are the undesired effects of an agent's action that can occur in addition to its intended effects. And these side effects are inherently challenging to identify before the system is deployed. For example, an autonomous vacuum cleaner or Roomba, it locked into the hair of a woman who was taking a nap on the floor in South Korea. The Roomba mistook the lady's hair for dirt and it locked onto it. An autonomous vehicle that was operating in the streets of Boston was stopped by a fleet of seagulls. The car mistook these unflappable birds for obstacles and it came to a complete halt. Another Roomba ran over animal feces in the house and continued its cleaning cycle, meaning that it smeared the mess all over. Amazon's Alexa started ordering doll houses for people after hearing the phrase on television. So these are some of the examples of negative side effects in the real world that have been reported recently in news articles. These systems are optimizing legitimate objectives that align with how we want the systems to operate. For example, We want the self-driving car to come to a complete halt when it encounters an obstacle. But then in this case, it lacked the knowledge that it can just edge forward to scare the bugs and then continue driving. In fact, they had to program this knowledge explicitly at a later point. So this shows that very often the designer of the system may have overlooked certain details that are important. In general, during the development phase, the designer tends to ensure that all the details that are relevant and necessary for the agent's task are included in its model. But then the other details may have been ignored for various reasons. But these details could start impacting the agent's performance after it is deployed. The missing details, for example, could arise because of the cultural differences. In the case of the Roomba locking into the hair of a woman, this issue was not discovered until the product was widely deployed in Asia, where it is relatively more common for people to take a nap on the floor compared to the rest of the world. Or the missing details could arise because of unexpected domain characteristics. It's not very often that we encounter seagulls in the middle of city traffic. Similar to how the side effects of a medicine are not the same across individuals, the side effects of an AI system also depends on multiple factors and are not easily generalizable across settings. For example, the side effects could depend on the system's capabilities and its core functionality. It could depend on the environment in which the system is deployed and the task that is assigned to the system. Of course, it also depends on the user preferences and tolerance, and meaning that to what extent we are willing to tolerate mistakes of AI system. So with that, I want to move on to part 2 of this talk. And in part 2, I want to focus on how users are responding to negative side effects of AI systems. So this is a good chance to ask any clarifying questions if anyone has. Okay, I'll take that there's no questions and move on. So as far as we know, there was no prior study that focused on understanding user attitudes towards negative side effects. So we know that there are negative side effects that are occurring, but we wanted to make sure if users really cared about this as a major problem that needed to be addressed. So we conducted the first study with 300 participants on the Amazon Mechanical Turk platform, and we had 2 different surveys. One that focused on side effects in the autonomous vacuum cleaner or the Roomba domain, and the other that focused on the side effects in an autonomous vehicle domain. So for each of these surveys, we had about 183 valid responses. For the Roomba, we focused on side effects such as the Roomba spraying water on the wall when it's cleaning the floor. And for the AV, we focused on 2 different forms of side effects. One where it could drive fast through potholes, resulting in a bumpy ride for the passengers.
Anna, yes, sir.
Was that a question? Sorry.
No, I think it was just a mistake.
Okay,
So.
okay, got it. So the other side effect that we considered for the AV is where the system would slam brakes at stop signs that could cause sudden jerks to the passengers. So one of the specific aspects that we wanted to investigate in the study was user tolerance to side effects. We know that when the side effects are safety critical, users will not be willing to tolerate them. So it's important that we take the system or suspend the system from its deployment and immediately address this issue. But in reality, many of the side effects could have some moderate to significant impacts, but they would not necessarily be safety critical. So we wanted to understand how users are responding to such side effects. So we asked the participants to self-report their tolerance level between low, medium, and high, where low indicates that they would stop using the system because of the occurrence of negative side effects. Medium indicates that they would continue to use the system, but would probably use the system less frequently. And high tolerance indicates that the usability of the system is unaffected by the occurrence of negative side effects. So here we can see that for the Roomba domain, about 23% had low tolerance. For the AV bumpy domain, about 12% had a low tolerance. And for the AV sudden jerks domain, about 42% had a low tolerance. So these results show that, as expected, the tolerance varies across settings and across participants, and it depends on the severity of the impact produced by the system. We were also interested in understanding how the user's trust in the system's capabilities could be affected by the occurrence of side effects. So again, we asked the participants to self-report their trust level between low, medium, and high, where low indicates that they no longer trust the system to be capable of completing its task because it's producing side effects. And medium indicates that the trust is affected, but only if the system does not adapt over time. And high indicates that their trust is unaffected by the occurrence of side effects. So for the Roomba domain, we see that about 34% have medium trust. And for the AV bumpy domain, about 60% had medium trust. So these are the fraction of users who wanted the system to be able to learn about side effects and adapt over time, even if not immediately. And this emphasizes the importance of developing mechanisms to mitigate negative side effects. But why is this a very hard, challenging problem? The first reason for that is because in many instances, the system requires broader background knowledge beyond what it already has, which means that it might need feedback to gather this knowledge about the side effects that it produces. In some problems, these side effects may be irreversible, meaning that once it occurs, there is no way to fix it. And it could be unavoidable when the agent is trying to complete its task, which means that this would introduce a trade-off between optimizing the agent's assigned task and minimizing the negative side effects. While all of these can be addressed by model revisions, this is a very expensive process and is generally very hard to verify. In fact, a user study shows that users are willing to take part in the process and assist the system in trying to mitigate the negative side effects. So we asked the participants if they are willing to provide feedback every time they observe negative side effects, or if they are willing to reconfigure the environment. For example, they could just move a furniture to a corner of the room when the agent is operating so that it doesn't produce side effects. Or they could specify regions of operation where they trust the system to be capable of operating without producing any negative side effects. So results show that users are generally willing to make use of all the tools, but they're more enthusiastic about the feedback approach. And it's likely because of the simplicity of interaction with the system. For example, in our survey, users only had to press a button every time they observe negative side effects so that they can provide the feedback to the system. So it's likely that because of the simplicity, users are generally more willing to use the feedback approach. So given this, that the users are willing to assess the system, how can we develop mechanisms to learn about negative side effects from feedback? So to that end, I proposed a technique that uses a multi-objective approach to identify and mitigate the side effects. So the agent's primary objective is to optimize for its assigned task. And the secondary objective is to minimize the negative side effects. So there's a lexicographic ordering over the objectives. And a key advantage of using such a lexicographic ordering is that we can now quantify the side effects and the value of optimizing the task in completely different units. For example, optimizing the assigned task could be measured in terms of the time taken to complete the task, and we can choose to quantify the side effects in a very different scale. So that's one of the key advantages of using this approach. So to further facilitate minimizing negative side effects, we also allow for a slack here. Slack meaning it's the maximum allowed deviation from the optimal value of the agent's assigned task. So let me quickly illustrate that with an example. So consider the setting here where there's a robot in an indoor setting. It has to quickly push the box from location 1 or L1 across the room to L2. And since it's required to push the box as quickly as possible, it's always going to push the box in a straight line, such as the one that's shown here along the red dotted line. And let's say the agent takes 10 minutes to complete this task. But in the process of pushing the box, it could dirty the rug as a negative side effect. But since the agent is always required to optimize its task, there is no way it can avoid the rug area. So there's no way it can avoid the side effect of pushing the box over the rug. So let's allow for a slack of 5. So the agent can now take up to 15 minutes to complete the task. So here we see the different dotted lines that are indicating the various trajectories that allow the agent to push the box within 15 minutes. Notice the green lines, however, completely avoid the rug area, which means that if the agent chooses to push the box along one of the green lines, then it can complete the task within 15 minutes and simultaneously avoid the negative side effects of pushing the box. But for the agent to be able to select one of those green trajectories, it needs to have a slack of 5, and it also needs to have knowledge about what are the side effects of its actions. And in many cases, the agent may not have any prior knowledge about its side effects, in which case it can gather this information through various forms of feedback. So one such form of feedback is called the approval approach, where the agent is going to select state action pairs at random and query a human who would then approve or disapprove the action execution in the state. So every time the human disapproves the action, the agent is going to map it to a high penalty and associated with the occurrence of side effects. This is a very simple approach and quite effective, but the disadvantage is that users may not be able to provide feedback on randomly selected state action pairs. So we consider a different approach called the corrections approach, where the agent is going to perform trajectories of its policy with constant human supervision. And then every time the human observes an action that is undesirable or unacceptable, they're going to stop the agent and prescribe an alternate action to perform. For example, if the agent was trying to turn left, they could stop the agent and prescribe the right action, asking it to turn right instead. So that's one of the examples of corrections. So every time the agent is being corrected, it assumes that its actions are resulting in side effects. This is a very effective approach, except that it requires constant human supervision. So another approach that we considered is learning from demonstrations, where the agent would observe the human perform demonstrations of how to complete the task in a safe manner. And then the agent would compare what it observed in the human's trajectories with its own policy. So every time there's a mismatch between what the human performed and how the agent was planning to do it, it maps those actions to a high penalty to learn about the side effects. Finally, the agent can also autonomously explore the environment and gather reward signals about negative side effects. So our overall approach operates in 3 phases. First is the data collection phase, where the agent is going to gather information about negative side effects, and then it generalizes this to new states and new unseen situations by learning a predictive model of negative side effects. And then it's going to update its existing model and solve it so that it can now compute a policy that will allow it to complete its task given the slack while simultaneously minimizing the negative side effects. So this is a simple policy visualization of the box pushing setting that I discussed earlier. So the agent has to push the box across the room towards the blue area. The video on the left shows that it's trying to push the box, but it uses the rug area, so it could dirty it. Excuse me, I'm trying to skip this. So sorry about that. Charger got disconnected, sorry. So the video on the right shows that the agent is now successfully learned to avoid the rug area, and it chooses to push the box completely around the rug area. So here in the case of learning by exploration, we see that irrespective of the number of trials, the number of episodes that the agent is allowed, it's able to successfully learn to avoid the side effects. But then when we allow the agent to learn from human feedback, different types of agent behaviors emerge. For example, with the corrections approach, it's able to avoid side effects with a budget of 100. But with the demonstration approach, even with a very high budget, it's not able to avoid the side effects. So this is actually showing us that some of the feedback approaches may not be as useful or as efficient in helping the agent to avoid the side effects. And one of the reasons for this is because that there could be implicit sampling biases in how the agent is learning about negative side effects with different feedback approaches, and that could significantly impact its performance. But we don't have to restrict ourselves to just the human feedback. In fact, they have a very rich and broader knowledge that we should be able to utilize efficiently to minimize the side effects. So we consider a human agent as a teamwork. So we have a formulation where the agent is optimizing its task and could produce negative side effects. And then there's a human agent who's going to now actively assist the system in beyond providing feedback and trying to mitigate the side effects. So they work together as a team, but they have different objectives. And one way for the human to assist the system is by performing what we call as environment shaping. Environment shaping is the process of performing reconfigurations of the environment so that the environment is now more agent-friendly and it doesn't produce side effects. For example, in the case of pushing the box, the human could just add a protective sheet over the rug. And now, even though the agent is not changing its policy, it will no longer damage the rug area. So this is a simple example where by making minor modifications to the environment, the human can help the agent in successfully avoiding the side effects. In fact, our user study shows that in general, users are willing to perform environment shaping, and some of them are even willing to purchase the tools if it is not provided by the manufacturer. So we formulate the process of environment shaping as an actor designer framework where the designer, every time the actor's performance is beyond their tolerance for negative side effects, they will select and apply some modification to the environment that maximizes their utility. And every time the environment has been updated, the agent is going to compute a new policy. And there's also a slack on the agent's performance. So what this means is, for example, the designer may have built a wall or come up with certain modifications that prevents the agent from even completing its task because the designer didn't know that it would have those consequences on the system's behavior. So by every time the agent's policy is now violating the slack, the agent can inform the designer that the modification that they made to the environment is not really agent friendly and it is not allowing the agent to complete its tasks. So the designer, though they wanted to be a collaborator and be an ally, they were actually acting as an adversary without their own intention or without their knowledge. So this framework allows the agent to communicate every time the designer is performing certain modifications that are actually hindering or negatively impacting the agent's performance. So our algorithm for this is there are two phases. There's a planning phase when the agent is computing the best way of going about finishing its task. And there's a shaping phase where the designer is actively performing modifications to the environment if necessary. So again, this is an illustration of our algorithm where in the planning phase, given a 2D map or a similar environment configuration, the agent is going to compute the best way of going about completing its task. And the human is going to perform modifications if the agent produces side effects that are beyond their tolerance. And this process continues, it repeats between the planning phase and the shaping phase until the agent's trajectories no longer produce any negative side effects or until there are no further valid modifications that can be applied to the environment. So here we consider the case where the entire floor is covered by a rug and the agent is expected to push the box as quickly as possible from L1 to L2. So irrespective of how many feedback we give to the agent, it's not going to be able to learn to avoid the side effects because all of its trajectories will result in negative side effects. But if we allow the human to take part in environment shaping, then we can see that they are able to avoid the side effects after observing just 2 actor trajectories. In fact, we see a very similar performance even when the entire floor is not covered by a rug. So we see that performing environment shaping is a lot more effective than providing feedback to the system. So to summarize, I introduced the problem of negative side effects. We formalized it for the first time in the works that I presented today. And we also discussed how it could affect the safety and reliability of AI systems. And these side effects are, in many cases, inherently challenging to identify before the system is deployed. So it requires principled approaches and tools that allows the agent to recognize the side effects, learn, and avoid the negative side effects of its actions. So to that end, I discussed two different approaches. In the learning from feedback, the agent is playing a central role because it's learning about the side effects and updating its model. And the human is basically in a more passive role because they are only facilitating this process. But in the environment shaping approach, the human is taking a more key role because they are actively performing modifications to the environment. And the agent is only responding to it because it only updates its policy in response to the environment reconfigurations. So these two approaches are somewhat complementary in the agent's responsibilities and the assumptions that we make about what knowledge is available to the agent. So this also shows that human can either play a passive role or they can be more actively involved in trying to improve the reliability of an autonomous system. Many of the side effects and the problems of negative side effects early on were discussed in the context of some toy problems. That was primarily because we did not have reported cases of negative side effects in prototypes or in deployed real-world systems. So to promote the evaluation of techniques on more realistic benchmarks, we have come up with a public repository of negative side effects where anybody in the AI community and the public can report negative side effects, and that will be evaluated by our team before adding it to this repository. Our hope is that this would be useful to AI researchers so that they can develop techniques that make more realistic assumptions and that are useful readily for the systems that are being deployed in the real world. I want to conclude the talk, but I'll leave this slide on in case anyone has any questions. Thank you for attending my talk today.
Yeah, thanks for the interesting talk. Does anybody have some questions that they can, there was one, okay, yeah. Looks like Colin, if you just want to unmute if you can and ask your question, that would be great.
Being heard? Oh, it sounds like I'm
Yes.
not. Oh, am I?
Yes.
Oh, okay, good. Yeah, right. So the feedback mechanisms you talked about during this talk seem to be focused on single user preferences, learning the preferences of a single user and using that to guide an agent away from negative behaviors, right?
Right.
Have you done any work on using the preferences of a population? So the sort of social choice theory aspect of that is sort of what I'm interested in.
So that's a great question. There's some pros and cons to aggregating user preferences. So if you look at this problem of side effects primarily as allowing an agent to be able to adapt its behavior more and customize itself towards the user and the target environment where it is situated, then we have to be very careful when we aggregate the preferences of other users who might, the preferences could be coming in or the feedback could be coming in slightly different target deployment areas.
Right.
So we have to be very careful. And if we have that knowledge, then of course, there's definitely a lot of utility in trying to generalize and quickly learn about negative side effects.
Right.
So we were considering, or we were at some point studying how we can aggregate the preferences of different users, aggregate the feedback from different users. And one way to do that is by determining how, basically adjusting the risk sensitivity of the system. So if we want the system to always be risk averse, then a simple thing to do is anytime there's a feedback from any of the users that this is a negative side effect or potentially a negative side effect, we want the system to try and avoid it as much as possible. So it's easy to have a risk-averse behavior, but it is slightly more difficult to accurately encode it in a way that is amenable to the individual user preferences, but still aggregating the feedback from multiple single individuals. unless we have additional information about the kind of environment, the exact setting where it produced the side effects, the time
Right.
and environment that led to the feedback and so on.
Mhm.
But that's definitely worth exploring, especially for systems like autonomous cars, because
Right.
the driving patterns could be similar across multiple areas.
Exactly. Yeah. Excellent. Thank you so much.
Thank you so much.
Yeah, so do we have any other questions from the audience?
Yep, I have a question. So yeah, thanks for the great talk. Like, it's very inspiring. And I wonder, like, so have you ever considered the cases like two user feedbacks are colliding each other? So if the agent learns the one feedback and later on the human wants the feedback B, but they're colliding each other, so that in a longer term, like there could be a catastrophic forgetting problem or something like that.
Great question. So I think this also goes back to the previous question that was asked about trying to aggregate feedback and preferences in a safe way. And that's actually one of the open challenges that we have in this space, that when we're trying to mitigate some form of negative side effect, we have to be mindful that it is not introducing any other risks to the system. It could be the same side effect, but that occurs in a very different setting, or it could be any other safety critical errors that were not accounted for early on. So that's something that's still an open challenge, but that's also an important problem to study in this space.
Thank you.
Thank you.
Yeah. Any other questions? I believe, yeah, we still have some time. Yeah, I was kind of curious. This is just maybe digging into the vocabulary too much, but probably you probably hear this from others. But the term side effect is in some sense overloaded, I think, for some of your algorithms, in the sense that you know, we're saying, you know, don't do this action, do this action. Like that's a form of feedback, and that could be based on just preferences, or, you know, what preference you want, or I want you to, you know, just do it this way because it's more efficient, versus, you know, you're spilling paint on the floor or something. That's a negative side effect. Do you actually distinguish, I guess, in your mind or in anywhere in your algorithms? I guess that's two places, this notion of negative side effects versus just any other type of preference information.
Great question. So the short answer is a yes and a no. So let me elaborate on that. So we assume that there's a function, but that's initially unknown, that maps that certain trajectories of an agent could result in certain forms of undesirable behavior, some of which are negative side effects. And what we mean here by side effects is the human's preferences are typically with respect to the primary task of the system. And if the human does not have any preferences in terms of how it should complete the task, because the system is always trying to optimize it. So it's always trying to find an optimal policy to complete its task. But if the user's preferences are not with respect to the optimality of the way in which the system is performing its task, but in terms of other forms of impact that the system's actions could have on the environment, then we treat that to be the side effect. So in some sense, we could say that a missing common sense knowledge could result in negative side effects. But again, that's a very broad spectrum of what the missing common sense knowledge. So I don't want to get into that. But for now, we are formalizing it as certain types of undesirable behavior that are not directly relevant to the task itself. For example, if there were no human in the environment, or if there were no other agent in the environment, then certain types of agent behavior may not really be considered as negative side effect or undesirable anymore, because it's perfectly fine for the system to go about finishing its task that way.
All right. Thanks. Yeah. Any other questions? It looks like Dragos, did you unmute?
Yeah. So, you know, two questions and one ties to Alan. So why don't you think in terms of planning and execution? And I think what you call side effects is actually the effects you observe simply at execution. And it's not only negative side effects that you care about, it's basically all side effects. I mean, something good can happen and you haven't planned for that. Can you comment on that?
Yeah, so there, of course, there are positive, negative, and neutral side effects. We could plan to amplify the positive side effects, but the care more is on trying to minimize the negative side effects as opposed to trying to amplify the positive side effects. And primarily that's because we want to be careful about the kind of systems that we're deploying in the real world and make sure that they are not having any adverse impacts that we did not account for or we did not anticipate early on. And that's why the focus of this work has been primarily on trying to mitigate or avoid the negative side effects as opposed to trying to learn about the positive side effects that the system could have. But that's definitely an interesting direction to explore on how we can identify or even categorize a side effect to be either positive or negative.
So what I meant was not so much, positive and negative.
Mm-hmm.
Side effects is something that you observe at execution simply. And you have to handle them. And, as you mentioned, the reward is delayed, right? And can you comment that? So your planning is basically you plan for everything and then you execute. Can you comment on what could be done in planning to handle this kind of risk that is observed only at execution?
So if we have knowledge or some prior distribution, for example, to say that it is likely that certain types of undesirable behavior might occur, then it is possible to account for that during planning. But if we have no idea, and if we treat these side effects as unknown unknowns that are discovered only after the system is deployed, then we completely rely on the system's ability to learn about this and quickly adapt its behavior once it's deployed. And there's very little that we can do in the planning phase unless we are willing to remove the system from deployment and then go back and fix the agent's model.
Thank you.
Yeah. Oh, looks like we have, Sandhya, you can.
Yep. So yeah, thanks for the nice answer. I think it's getting really interesting and I really tempted to read your paper more. So one thing I'm just wondering, like, do you have you had any chance like to evaluating like how much certain feedback is valuable? For example, like if I'm raising my child and giving always the negative feedback, then like it won't make the child how do I say, like fully functioning. So there could be some mechanisms like you can value, like you can decide how much value the feedback will be given the state. So like, have you ever considered these kind of questions in your research?
It's a good direction that I haven't given too much thought about until now. But something that I've been thinking about now is, so in my work so far, I assume that the human is committed to providing feedback in a certain format. If they're going to demonstrate, it's only demonstrations. If they're going to approve or disapprove, it's always the same. But there's no necessity to assume that. In general, when humans are interacting with another human or with an AI system, it's likely that we would be making use of different types of feedback mechanisms, some more useful than the other. So can the agent aggregate the information from different forms of feedback and learn effectively from that? Some could even be intermittent, for example. So that's one of the directions that I'm currently interested in pursuing. Not quite what you were asking me, but that's definitely something that I want to think about since I'm now looking at aggregating different forms of feedback.
Thank you very much. I'll look forward to it.
Thank you.
Do we have any other questions before I usually like to ask a final question. It's not going to be too, well, it might be hard. I don't know.
I think there's a question in the chat about how much feedback is required to learn a new policy to deal with side effects. So I think that's hard to say or hard to quantify without additional information, because it could depend on the magnitude of the side effects and how large the problem space is or how complicated the environment is. And certain types of feedback are generally more effective in allowing the agent to quickly learn about side effects than few other forms of feedback. So the short answer is I don't know. The long answer is it's hard to quantify.
Yeah, so I guess, yeah, I'll ask the final question, although if something comes to mind, you can ask, somebody else can ask the final question. But so yeah, we hear a lot today about places like Facebook, and I mean there are pinata right now, but you know everybody has this issue of side effects of algorithms for recommendation. Like that's the most basic thing, and this is been well known for a long time. They make us angry, or so it seems like an interesting case study for your two approaches here. If you were to go to Facebook, please don't go to Facebook. I'm assuming you don't want to go to industry right now because you would already be there. But yeah, assuming you went to Facebook or Twitter or whatever else, which strategy that you've been looking at or some other strategy might you try to employ or recommend? This direct feedback or changing the environment, the mechanism?
Wonderful question. So I've been thinking about this for a while now, and the reason is the kinds of the types of negative side effects that I've been investigating so far are mainly what we can easily observe. But the kind of negative side effects that you were talking about are more latent in terms of how it could affect a human's emotion or climate change and things like that, that are not immediate and are more latent until much later in the process. So I'm interested in extending or studying more in detail about the side effects that in various settings like healthcare, recommender systems, and so on, that do not produce negative side effects or visible negative side effects immediately, but could have long-term impacts. I don't know what would work there yet, but that's something that I've been thinking about for a while now. And how we can even, because in those settings, it's not easy for the user to provide feedback because they themselves may not realize that it's having negative side effects until much later in the process, or they might not be able to pinpoint what is the source of negative side effect for a long time. So it's not even clear if we should rely or to what extent we should rely on human feedback in those settings, because we have to acknowledge that it's going to be a lot more noisier because humans may not be, or a lot of users may not be very competent in expressing feedback about their own latent emotions or latent features.
Yeah. Not to mention here, the negative side effects are highly correlated with positive side effects, or well, the positive
Yeah,
it's
exactly,
not, I guess it's not
exactly.
a side effect, the optimization objective. So,
exactly.
so might be hard to do anything if you work at Facebook. Cool. Good. Well, thanks a lot. This was a very interesting talk, very timely, and I learned a lot. And we will be back in 2 weeks with our next new faculty member. I forget which one, but you can look on the Tech Talk webpage, go to the main EECS webpage, and we have all the talks there. This talk is recorded and it will be posted, and all the previous ones have been as well. So thanks a lot. We'll
Thank you so much for being here today, and thanks, Alan, for hosting.
Yep, thanks.
Have a nice day. Bye-bye.